All right. Here I talk about corrections mainly from the point of view of gamma ray spectrometry, but of course these corrections can be used for alpha spectrometry too. So these are the main corrections: radioactive decay, self-attenuation or self-absorption, and coincidency correction. So, simplified equations that I showed you in previous lectures, they didn't take into account corrections. So, more precise equation is following and these corrections may be applied to this here and here. So, as I told you, these are the main corrections. So, radioactive decay correction goes mainly to that point, and also self-absorption, and also coincidence correction too. These corrections can be taken into account in different ways, depending on how the activities or activity concentrations are determined in practice. So, these correction factors can be computed separately, multiplied together, and applied as shown in the above mentioned equations. Some of the corrections, like the self-attenuation and geometry corrections, they can be or are computed by an efficiency transfer program such as FTRAN, which can be as a part of the analysis process. So you do not need to do corrections by hand. So the software can do this. So in Stuk we analyze typically 2,000 to 3,000 samples per year, and their characteristics are different. Different measurement geometries, different compositions, etc. So we are using FTRAN in routine basis. Let's look at the correction for radioactive decay. You know certainly this picture. This is timing, and this is number of nuclides in some sample. Starting point is 1 million nuclides in the or activity in the beginning of time. After one half-life, there is only 500,000%. Secondly, there are 250, etc., etc. But when you determine the activity, you have to select what is the correct time when you report your results. Is it here, here, or where? That's one of the key issues. So number of radioactive nuclide reduces as a function of time. You know these equations. You must specify the time to which you report the activities. Here is an example for air monitoring in case of continuous sampling versus separate sampling and counting. In case of nuclear power plants, they often use continuous air monitoring. And if we assume that the concentration of radionuclides in air, inside air or outside air, is constant, and if we use continuous air monitor and we start sampling here, it have activity in the filter behaves like this. After some time, there is a balance because of radionuclide decay. This happens in the case of separate sampling, and after sampling, we take counting. So here we take a sample, for example, 1 day sample. It takes some time to change the filter, and here we start counting by using alpha or gamma ray spectrometry. So, for example, in the case of CTBT organization, this time here, it's, if I remember this correctly, it is 1 day. Why? Do you think why they do things like this? So there is 1 day decay, and question is air sampling and then detecting possible gamma ray emitters in the sample. Why 1 day? All right, I will explain. The reason is that sorry, there is radion daughters in the air, short-lived ones. You remember lead-214, bismuth-214. So they want better background, as low as possible, and within 1 day, these nuclides, short-lived nuclides, has decayed off. So, when counting starts, and ends here, to TC, you can see the text here, or you cannot see the text, but it's basically you can see the text later. But typical reference time is in the middle of counting time, or in the middle of sampling time. Depends on the cases. So, because of this behavior, we have to correct decay. So counting correction C1, which is this one, it compensates the decay during counting, where T is the counting time here, and T is the half-life of the nuclide in question. And counting during the waiting period, C2 compensates for the decay before counting. Here. This TW, it's the waiting time. So if you want to calculate these corrections by hand, it's of course possible by using, for example, this program. There are a lot of applications in it. This is one example. So you perhaps know these Bateman equations. It's a full descriptions how radionuclides, I mean the series of radionuclides, are behaving as a function of time. But commercial spectrum analysis software usually incorporate almost all these corrections. Let's look at the correction for self-attenuation. So in terms of metrology, the gamma ray spectrometry is a secondary method, which means that calculating the activity of the sample interest, the result is compared to that of the calibration, so calibration standard. And the point is that usually the sample characteristics are different compared to those of the standard, at least in our cases. So in Stuk we are measuring so many different type of samples. It means that attenuation of gamma rays in the sample itself is different. So as you can see here, we can call gamma behavior like this. It's a self-absorption. In this case, we can call self-attenuation, which are more or less same thing here. However, energy of this gamma is different than the original gamma. So this doesn't go to the full energy peak. So different attenuation may be due to different sample size, I mean diameter and sample height, different sample density, and of course different elemental composition of the sample. There are two main concepts that deal with this area. Linear attenuation coefficient. It quantifies attenuation per unit length, for example, per centimeters or millimeters or whatever is the unit. However, mass attenuation coefficient is more useful because there is independence of the material density. So here is mass attenuation coefficient here, and this is energy. There are different materials here. For example, soft tissue is here, bone is here, and heavy materials here. For example, this black thick one is lead. Any ideas why in these fat soft tissue or bone cases there are no these edges? Any ideas? The binding energies of electrons in the electron cells. So the energies are low that they are not visible here. So as I have explained several times, knowing the elemental composition is important, especially for quite low gamma energies. Oh, this is interesting case that I think that I showed this or discussed this yesterday or day before that. Some years ago, I got a sample from a mining company. They gave me a beaker full of gold. The value was very, very big. In fact, they wanted to know what kind of radioactive materials, natural radionuclides of course, are in these samples. So, previously when I went into my lab almost 10 years ago, our efficiency calibration didn't take into account elemental composition in small energies. It took into account sample thickness, for example, and sample density, but not elemental composition. Then I used this, our old system, and the result was for the peak efficiency was this as a function of time. But now the composition is totally different compared to our normal samples, because usually we don't analyze so dense samples. I used FTran software, and this was the result. So if I have used our normal way to analyze this spectrum, I would get totally incorrect result at small energies. And in this case, small is below 700 kilo electron volts. Now you can clearly see the effect of elemental composition. All right, let's look at briefly coincidence correction things. I explained this once more, but let's do it again, because this is not an easy thing. So, this is cobalt 60 decay scheme. It goes to the nickel 60, and you can see here the decay times of these levels. So it's of the order of picoseconds half-life. However, typical time resolution of electronics, it is order of microseconds. So it may happen that both of these pulses come to the detector at the same time. So what happens is that detector doesn't see that one, it doesn't see that one, it sees this one. 3 plus 1, 3, 3, 2 is this. Okay, it might happen like this also. That, for example, let's go here. For example, this energy was totally absorbed in the detector, but the second one goes like this. So this is the reason of these. Because there should be, if there is no background, there should be no higher energies than this one. Coincidence correction is small when there is large source to detector distance, because if the distance between the detector and the sample is large, it's quite improbable that photons go to the detector at the same time. Coincidence correction is notable for well type of detectors. In well type of the detectors, there is a hole in the detector into which you can put the sample if you want. In some cases, gamma X-ray coincidences must be accounted for, especially in case of electron capture. I hope that your analysis software, Jenny, is able to calculate coincidence corrections. I think it can, but there are several other computer programs, such as this EFTRAN software, Etna, for example. They can calculate coincidence corrections. Correction can be calculated by the aid of total efficiency, but usually they are computed by using a specific software. In case of a point source, this is the total efficiency. Oh, I said previously that I send the www pages, the name of the www page to Karunakara. It is shown here. So you can download it free of charge if you want.
Downloaded it available in some of the computers.
Yeah.
Some of you want to go and work, you can do that.
Yeah. It's a learning process. I mean, learning how efficiency behaves in different cases. So this is an example if we don't take into account coincidence correction. So this is energy here, and this is peak efficiency here. The maximum value is, of course, 1. This was our old efficiency curve as a function of energy. Nowadays, it is more or less same. There are no big changes. However, when I did this efficiency calculation, these are the nuclides shown as red arrow, which do not have notable coincidence corrections. For example, lead 210, and also cesium 137. They stay quite well to the curve. However, there are some nuclides, like cobalt 60, these two peaks here, they do not fit the curve. But if I take into account coincidence correction, then they are located here. So this is not fitting of these measured efficiency points. This is our old curve, which is quite good also. You can see also here the uncertainties of each point. Okay, I don't go any further for the corrections. There are some minor things that can be taken into account or not. This example I already showed you. It was yesterday or day before. And please, if you like, study EFTRAN. For example, this kind of case. Filling height, in our standard case, 2 centimeters. And if the sample contains, for example, 1 millimeter water, we can see the difference between the efficiencies. So this was my last slide, and the presentation was quite short because originally when I saw the brochure, the timing was a little bit different than the timing in the present program. I have one more presentation still, but do you have any questions about these corrections or comments? Oh, if not, I suggest then we could have a small break. Is it? Let's see.
You will appreciate these concepts once you start working in the field, because these are very important. This efficiency correction, because you can't have a reference material in all types of geometries.
Mm.
So efficiency transfer process or calculations are going to be essential at some point of time in your career.
Yeah.
So it is very important. You should appreciate it.
Yeah. But please note that there are several other programs that can calculate efficiency transfer or full Monte Carlo codes.
Yes.
But in the case of full Monte Carlo software, the point is that you have to very precisely know characteristics of your detectors.
Yeah, almost all the supplier will tell you whether you want basic version or the advanced version. Mark the region of interest and take the count. The advanced version will also, for example, Guinea, which we are using, has a option called Geometry Composer. So it does exactly same. So you can compose the you are going to use. The corrections for the efficiency for a sample which is in another geometry. So other software also have. This appears to be a very user friendly.
All right, should we have a 20 minutes break or so we can?
Yeah. Container 2. There is a point, container 2 absorber gap, the last one in the source. Go down, this one.
Yeah. Container to absorber. All right. So, in some cases, for example, in the case of CTBTO organization, they do not want to see low energy gammas for some specific reasons, which are, I think, a little bit political. But let's forget that thing. They put an extra absorber, which is shown here, above the detector. This absorber prevents low energy photons to go into the detector. And this container to absorber gap, well, in this example case, this is just an example, it's a distance between the sample and the absorber, 3 millimeters.
So you mean to say there is another layer of a material between the sample and the detector?
Air.
Air.
Yeah. This is just an example. Of course, normally we put the sample just above the absorber, if any. We are not using any absorbers in Stuk.
I have one question. Aluminum detector.
Yeah.
And you have a composite entrance window, composite carbon entrance window.
Yeah.
Do you keep the sample right on the window, or you keep a support over that?
No, it's practically right on the window, but this distance, I mean distance between the active part of the detector to the source itself, it is very important in terms of efficiency.
Yeah.
We have some broad energy germanium detectors, and they look like this. Sorry, I enlarge the detector a little bit, so it's like this. There is a small thin metallic ring here. This is some metal. I think it's aluminum here. And in some cases, our samples, our beakers are bigger than the detector. So size like that. All right. But the point now is that this window is very thin. 0.5 millimeters or so. I don't remember the exact number. But if you are looking it this way, the point is this. So this is the part of the metallic ring, and the window goes like this, in fact. And this is because of the vacuum inside the detector. Why there is vacuum? Do you have any idea? Because in the very bottom there is this long finger made of copper and minus 200 degrees centigrade there. So vacuum is like an insulation. If you lose the vacuum, then you have a problem. In this case, when we have a small sample, like a small beaker, like this one, then the distance between the detector is located here. So there is a difference between this distance compared to this case, because bigger beaker goes there. And this distance is in fact very, very important. Believe it or not, you can use FTRAN software to test this. Because sometimes it may happen that you have a very radioactive source, very active source, and you have to put this detector sample here. And you can use FTRAN software to correct this distance. Is this the answer of?
Yeah, partially. Carbon window.
Yeah.
What could be the maximum mass? Can I place a 500 gram sample right on the window?
I think some 100 grams are okay, but I cannot exactly say the number. I know that some of my colleagues accidentally dropped some beaker there and the window broke down,
Yes.
then it was a very expensive repair.
Correct. So that's why, you know, if you have observed our detector, we keep a polyethylene cap on that just to protect the window. But case there's ample light on the window. But we don't want record he has 18 detectors, but we have only 3.
Yeah.
So we want to take care of it.
Yeah, some detectors has aluminum housing here,
Yeah.
and
They are
then
ready.
it's
Yeah, they are ready.
yeah,
But then with the aluminum windows, it cuts off the low energy count.
yeah. All right. Any other comments, please?
Yeah, if there are no comments, discussions, this
For 20 minutes, then it's exactly 11 o'clock when we go back
Yeah.
here.